Okay, welcome to lecture 27. So in this lecture, we're moving on to unit 4 of the class. So we're testing, we're looking at systems of linear first order equations. Okay, and so systems of equations are really important because, for example, if you have a mixture of chemical species, then in fact you'll usually have one ODE for every chemical species. Okay, so differential equations can describe, a single differential equation could describe how one chemical species changes over time as it reacts, but a system will explain how all of the chemical species are reacting with each other. Okay, and so this also occurs quite often in systems like predator-prey systems, or let's say systems where we're modeling how a population will evolve over time. So for example, you may have a population of one type of animal that grows over time because they're breeding, but then that population of animals is being eaten by, let's say, a bird of prey or something, and so we have a second dynamical system which will be represented by a separate ODE. So we often in real applied practical problems have multiple ODEs that we have to solve simultaneously. Okay, so what we're going to cover in the lecture today is something called matrix form. So we're going to take this system of ODEs, so these multiple ODEs, and write them in a matrix equation. And then we're going to cover some theoretical aspects of systems of linear ODEs. Okay, so if we have n ODEs, then we can represent them by n equations, right? So we're talking about linear first order ODEs here. So we have dx1 by dt equals some equation, dx2 by dt equals some equation, all the way through to dxn by dt. Okay, one key point here is that the independent variable in all of these equations is t. Okay, so we have the same independent variable in all these equations, but of course different dependent variables. So we have x1, x2, all the way through to xn as the dependent variables. Okay, and in each of the equations, each of the dependent variables can occur as long as they occur linearly. Otherwise, we would not have a linear system. So, for example, in this first line here, dx1 by dt, x1, x2, and through to xn all appear linearly. Okay, there's no x1 squareds or anything. And similarly, if we check every line, in fact, dxn by dt, x1, x2, and xn all appear linearly here. Okay, and multiplying each of the dependent variables is some coefficient, right? So we have a11t here, a12t here, and so on. Okay, and again, those coefficients have to depend only on the independent variable t. They could be constants, of course, but they have to not depend on the dependent variables. Otherwise, we will not have a linear system. And then finally, we can have some non-homogeneous terms here. So these are represented by the f1, f2 through to fn things here. And that just represents the non-homogeneous terms which may occur in some systems. Okay, so we want to write these system of n equations as a single matrix equation. So what I'm going to do is I'm going to define this boldface x. So I write it in bold because it's representing a vector. Okay, and this x here is going to be the vector of all the dependent variables. So x1, x2 through to xn. Okay, this vector f is going to be the vector of all the non-homogeneous terms. So all the f terms, f1, f2 through to fn. And then I'm going to define a matrix, an n by n matrix A, which is the matrix of all the coefficients. So if I, for example, look at the first row of this matrix A, this is representing all of the coefficients in the first equation. So A11, A12, A1n, A11, A12 through to A1n. And similarly for all the other rows. Okay. And so if you look at all the columns, these columns of values here, these are going to be the coefficients multiplied by x1. So A11, A21 through to AN1, over here we have A11 times X1, A21 times X1, AN1 times X1. And similarly, the second column in this matrix A will be all the coefficients that are multiplying X2, and so on. So if we define this matrix A and these two vectors X and F in this way, then we can represent the system of linear first order ODEs as a matrix equation. Okay, and that is a lot more compact than writing out each equation individually. Okay, so you might like to check or convince yourself that that is the case. But one key point is that if F is 0, and that is the 0 vector, not just 0, so if every entry in this vector F is 0, then we say the system is homogeneous. And we can write that as X prime equals A times X. The prime here, of course, denotes derivative, and because T is the independent variable for each of these equations, we can assume that means dx by dt. Okay. So let's look at an example here. We have two equations, or a 2 by 2 system. You'll note that we have x and y, and each of these equations appear linearly. So we have two linear ODEs, or a system of linear ODEs. They're both first order, of course. And we have in each of these equations, we have non-homogeneous terms, sine of t and e to the t. So I'm going to define my vector x to be the vector of dependent variables. So the dependent variables here are x and y. Well, we have t as the independent variable in both. And I guess one thing that I think is helpful is here I've written x first and y second. So in each of these equations, I think it's sensible to write x first and y second. X first and y second. I think that just keeps things consistent, and it avoids errors, or it reduces the likelihood of errors. Okay, well, the non-homogeneous terms here, of course, in the first entry here will represent the non-homogeneous term in the first equation, so sine of t. And in the second entry of f here will represent the non-homogeneous term in the second ODE. Okay, we can write down the coefficient matrix A here. So again, each row of A represents the equation. So the first row of A represents the coefficients in the first equation. The second row of A represents the coefficients in the second equation. The first column of A represents the first dependent variable. So 1, negative 2 here represents coefficients that are multiplying x. The second row represents coefficients that are multiplying y. So if I just take a closer look at that, the first column, the first row, represents x in the first equation. The second column, the first row, represents y in the first equation. So negative 5, negative 5. Down here, we have the first column, so that represents something multiplying by the first dependent variable x. In the second row, so the second equation, so negative 2 here. And similarly, 10. Okay, so you might like to check that dx by dt equals A, this matrix A times x, the vector x. So this is a matrix multiplication, so you have to be careful to calculate that properly, plus this non-homogeneous term f. Okay, so in the scalar case in units 1 and 2, where we were just solving one ODE, we had solutions. We had solutions which we often represented as x of t equals some function, some scalar function of t. For the systematic case, a system of linear first order equations, we actually have a solution vector. Okay, and a solution vector is any column matrix or any vector whose entries are differentiable functions and they satisfy the ODE on some interval. Okay, so any solution vector that satisfies this ODE is a solution of the ODE. And of course, whenever we have an ODE, we can always turn that into an initial value problem by providing initial conditions. So if we have an ODE, in this case a non-homogeneous ODE, if we also provide an initial condition, then we can turn this into an initial value problem. So for systems of linear equations, the initial condition is going to be a vector of initial conditions. So at time t equals t0, the solution vector x is equal to some vector x naught. Okay, and that vector x naught is a vector of constants. So these are our n initial conditions here. So if we have n equations, we must have n initial conditions. For example, if we had a 2x2 system or two equations, two linear first order ODEs, then we would need two initial conditions. Okay, whenever we start talking about initial value problems, we need to know that there is actually a solution that is unique to that initial value problem. So in the case of systems of linear first order equations, it's actually fairly simple. So all we have to do is check this coefficient matrix A and this non-homogeneous vector F. So it turns out that if A and F are composed or made up, every entry in those matrices, or this matrix and this vector, are continuous functions on an interval, then there exists a unique solution to the initial value problem. Okay, so for example, we don't want to have an entry of A, for example, being 1 over x, because then at x equals 0, this function is not continuous and there is no unique solution, or we're not guaranteed to have a unique solution for any interval containing that point x naught equals 0. So it's very similar to the first order case, sorry, for the scalar case. So any initial value problem, we have an existence and uniqueness theorem for this. We just need to check the entries in A and F, the matrix A and the vector F. Okay. If we focus now, though, on homogeneous systems for a bit, so where this vector F is equal to the 0 vector, so every entry in F is 0, then we have a homogeneous system. And similarly to the scalar case, where if we had more than one solution to an ODE, we could superimpose those solutions or combine them together linearly to form another solution. So for the case of systems, if we have solution vectors x1, x2 through to xk, if each of these vectors is a solution to the homogeneous system, then the linear combination of those solution vectors is also a solution on the same interval. So here, C1, C2 through to CK are constants. So this is very similar to the scalar case, except that in this case, our solutions aren't just scalar functions, they are vectors, solution vectors. So if we have multiple solutions to an ODE, we can use the superposition principle to form the linear combination of those solutions, and that is also a solution to the homogeneous system of ODEs. But of course, we also want to check if we have multiple solution vectors to our ODE, we want to check if these are linearly dependent solution vectors, because x1 could just be 2 times x2, which would make it dependent. So if we have k solution vectors to the homogeneous system x prime equals a times x, we can say that the set of these solution vectors is linearly dependent if there exists constants c1, c2 through to ck, which are not all equal to 0, such that c1 times x1 plus c2 times x2 plus all the way through to ck times xk equals the 0 vector. Otherwise, we say the set is linearly independent. Another way of saying this is that if we can write x1 as a linear combination of all the other solution vectors, then the set would be linearly dependent. If we can't write any of the solution vectors as a linear combination of the others, then the set must be linearly independent. However, you may recall from Unit 2 that the way we actually checked if solutions were linearly independent or not was using the Wronskian. Okay, and we can do that here as well. So I can form this matrix, which is made up of the solution vectors x1, x2 through to xn, and then I can take the determinant of that matrix. Okay. So again, just to be clear, this first column here is the first solution vector x1. The second column here is the solution vector x2, all the way through to xn. Or xk in this case, but okay, we'll use n. And if you recall, if this set is linearly independent on some interval, then the Wronskian of these solution vectors is not equal to 0. Okay, so if we take the Wronskian of these solution vectors and it's not equal to 0, then we're guaranteed to have a linearly independent set. So let's look at an example here. We have the system of two ODEs represented in matrix form as x prime equals 3, -4, 4, -7 times the set of the vector of dependent variables. Maybe that's x1, x2 or something. Okay, and well, so in the next class, I'll show you how to solve this system. But for now, I'm just going to tell you that two solutions to this homogeneous system of ODEs are the vector 2, 1 times e to the t, and the vector x2. The x2, a second solution, is the vector 1, 2 times e to the minus 5t. Okay, so I haven't told you how I've got those vectors. I've just told you that they are solution vectors. But what I want to know is, are they linearly independent solution vectors? So I can check this by calculating the Wronskian of these two solution vectors. So the first row in this Wronskian matrix here refers to the first entry in x1 and the first entry in x2. So 2e to the t, 2e to the t, e to the -5t, or 1 times e to the -5t. And similarly, the second row in the Wronskian matrix here represents the second entry in x1 and the second entry in x2. Okay, so now I can form this matrix here and take its determinant and show that that is not equal to 0. So I get 2 times 2 is 4, e to the t times e to the -5t, minus the product of e to the t times e to the -5t. So in fact, I think this should be 3 e to the -4t, but that doesn't really matter. The point is it's not equal to 0 for any finite value of t. So therefore, yes, these solution vectors x1 and x2 are linearly dependent. Sorry, linearly independent. x1 and x2 are linearly independent because the Wronskian of those two vectors is not equal to 0. Okay, well, now we know that for our 2x2 system, we have two solutions which are linearly independent. So if you recall from Unit 2, we can show that this is a fundamental set of solutions. Okay, and the same thing holds for systems of linear first order equations. If I can find, for an n by n system of equations, if I can find n linearly independent solution vectors to the homogeneous system on some interval, then we say that the set of these solution vectors is a fundamental set of solutions. So exactly the same way that the scalar case, if we had n linearly independent solutions to the scalar ODE, then we had a fundamental set of solutions. It's exactly the same here, except our solutions are solution vectors instead of scalar functions. Okay, and if we have a fundamental set of solution, then we can write down the general solution to the homogeneous ODE, or in this case, the system of homogeneous ODEs. So if we have the homogeneous system of linear ODEs, x prime is equal to a times x, and we have n solutions which turn out to be linearly independent and hence a fundamental set of solutions, then the general solution to this homogeneous ODE is just the linear combination of each of these solution vectors. So C1 times X1 plus C2 times X2 plus all the way through to Cn times Xn. So if we go back to our example, our 2x2 case here, so we had two solutions here, X1 and X2. We showed in an earlier slide by calculating the Wronskian of these two solution vectors that they were linearly independent. Therefore, X1 and X2 form a fundamental set of solutions. Therefore, the linear combination of X1 and X2 is a general solution to the homogeneous system of linear ODEs. So again, it's very similar to the scalar case. Okay, moving on to non-homogeneous equations now. So if you recall in Unit 2, if we had a non-homogeneous ODE, we could write that as the sum of a complementary solution, which was the solution to the associated homogeneous equation, plus a particular solution. And so the same thing holds for systems, in fact. We can split the general solution to the non-homogeneous equation up into a particular solution, XP, which is a solution to the non-homogeneous system. And well, we're going to show that we can find that using the method of undetermined coefficients. And so the general solution is the sum of this particular solution and the complementary solution XC, which is the general solution of the associated homogeneous system, x prime equals a times x. So exactly the same as in the scalar case, except our solutions now xp and xc are solution vectors. Again, all of the arbitrary parameters are only present in the complementary solution, never in the particular solution. So the general solution to the non-homogeneous ODE is the sum of the complementary and the particular solution vectors. Let's look at an example of that. So if we ignore this homogeneous term here, this homogeneous term is 3, 4, well, this is the same system as in the previous slide, except that we have this non-homogeneous term. Okay, in this case, the non-homogeneous term are just constants, but they could be functions of t, arbitrary functions of t, cosines, sines, exponentials, anything, polynomials, anything. Okay. So again, in a previous class, in a previous slide rather, we said that the complementary solution to the associated homogeneous equation is given like so: C1 times the solution x1 plus C2 times the solution x2. So we're going to learn in the next class how we can find that complementary solution. But to find the particular solution, what we're going to do here is use the method of undetermined coefficients. And so because my non-homogeneous term in the system of ODEs is just two constants, so 3 and 4, I'm just going to take my particular solution to be two unknown constants, A and B. Okay, so if I use my particular solution XP in my ODE, well, XP is we're going to have this coefficient matrix A times XP plus the non-homogeneous terms equals the derivative of XP. Okay, but the derivative of XP is going to be the zero vector because A and B are constants. So if I take the derivatives of A and the derivative of B, it's both going to be 0. So XP prime is going to be the zero vector. Okay, so I can write this out like so. So this gives us two equations for two unknowns. The two unknowns are A and B, and we can solve that, right? So we can write down the two equations like so, and where do these come from? Well, the first row here is associated with the first row in the matrix form. So 3 times A minus 4 times B plus 3 equals 0. And similarly, the second row comes from 4 times A minus 7 times B plus 4 equals 0. So you need to be able to go from writing a system of equations into matrix form and back again. I expect you to know how to do that. So feel free to practice that. Okay, so if I solve this system of equations, I should find that A is equal to -1 and B is equal to 0. And therefore, my particular solution, xp, is equal to -1 in the first entry and 0 in the second entry. Therefore, my general solution is equal to the complementary solution here, which has the arbitrary parameters, C1 and C2, plus the particular solution, the vector -1, 0. Okay, and I can pull out the first row and the second row of that matrix solution to write two solutions to the system, right? So the first row here, C1 times 2 times e to the t, plus C2 times 1 times e to the minus 5t, minus 1. Okay, and similarly for x2. So just to summarize what we've done here, we've introduced this thing called matrix form, where if you have a system of linear ODEs, then we are able to write that system in matrix form. And I would expect you to be able to go from matrix form to writing out the system and back again. We've shown that many of the theorems from Unit 2, including existence and uniqueness and the general solution to homogeneous systems, many of those hold from Unit 2. Okay, so they apply to systems of equations as well. We've shown that the method of undetermined coefficients can be used to find a particular solution, just like in Unit 2. And the complementary solution, well, I'm going to show you how to find that in the next class. So I'll see you there.